Hello everyone, thank you for joining me at PriCon. My name is Shang, and I lead the Rexus team at OpenMined. We're going to build and launch an AI-powered website that learns and optimizes its own UX over time. So the use case is actually fairly common. I'm a dev, I build a thing, I think it's the next big thing. And of course, there's nothing else to do but to put up a sign-up page and let everyone know and get everyone to sign up and use it. So the question is, what is the best UI to maximize user sign-up? Maybe at this point, your UX team comes to you and say, hey, here's the list of all the options. We're very sure one of these combinations will have a very high click-through, the other is not so much, but we don't know which option it is. At this point, you multiply out all the options and you're like, okay, there's 24 possibilities, and you're experiencing the curse of dimensionality. At this point, the immediate instinct might be to say, okay, let's do A/B testing, and that is a good solution. However, A/B testing could get very expensive. Consider this. You want to serve enough users to each options to get statistical significance. And usually this is in the order of thousands or hundreds. But let's say in our case, we want to essentially funnel 10 users to each option, each of the 24 options. And because only one of the options is optimal and the other ones kind of are not, what that means is only 10 users gets the best option, and then 230 of them got a suboptimal experience. This doesn't sound so bad, but when you consider how costly it could be to acquire each user in the real world, and also how costly it could be to lose the potential revenue, in the case of, let's say you're a large popular e-commerce company, the cost of each user over their lifetime could be in the thousands. This kind of gets pretty costly. So we would like a better option to do this, and we actually do. And the way we're going to do it is using a very simple version of reinforcement learning in the browser. We're going to make an algorithm that learns from user interactions. Here's how that might look. So over here, you go to a sign up page, and so far so good, looks pretty normal. Maybe you click sign up, maybe you don't, and then maybe you go to the website again, or the next user goes to the same website on their own browser. Immediately you notice something interesting, and that is the layout has changed. So let's take a look at what's actually causing this in the background. So what's happening here is that the browser is actually running SIFT.js, which is our federated learning library for the browser. What it's doing is that it's downloading a model from the central PyGrid server, and it's essentially learning from user interactions. For example, if I land on a page that is not colorful, I don't want to sign up, I can say no, and this reports a negative update. And if I land on a page and hopefully it's colorful, we can click on it, and that's a positive update. So far so good. So let's take a look at how the math actually works and why this is a good idea. So we're modeling the click-through rate of each UI option as a Bernoulli random variable, and we're going to initialize it with uninformative data priors. What this looks like is that initially everything is just a flat line. It's not very different because we haven't interacted with enough users to learn anything yet. This is also why when we're initially using this model, it's going to be fairly random. It will show you different layouts. But the question is, what happens after we're able to learn from 100 or 200 users? Do we actually learn preference? And here we set up an experiment where we initialize a vector of random numbers to represent user preferences. The only thing we're going to do is randomly select one of them and set this as the optimal option. So let's see what this looks like. So as you can see, we start with uninformed data priors, and very quickly we're starting to figure out, hey, one of these options is definitively better than the others. So let's see that again. This is how it looks. So far so good. So at this point, what you would expect is that if you go back to the browser, it's going to start to serve you the best option, and it will be acting less randomly. So let's take a look. So, yep, it seems to have converged. Once in a while, it will still, serve a random option to explore and update itself. So the benefit of using such an algorithm is that it's able to essentially adjust itself to user preference updates. So let's take a look at how this looks. So we're essentially simulating a user preference change, and we're going to run this again. So now observe how we're able to very quickly pick out that user preferences have changed. And just one more point to add, this is also an algorithm that is very amenable for adding options. Let's say your design team comes to you and say, hey, we actually have a 25th option that we think will be even better. What you could do is optimistically assume the 25th option, which you currently have no information on, is just as good as your most favorable option. And if it is not, it will quickly, the algorithm will quickly learn that it is not a favorable option and it will not be served. So these are some of the benefits of using this kind of algorithm. The last thing I wanted to point out to you is that how simple and how compact the update is. In fact, I can show you essentially the update, and that is all the code we need. We're essentially just doing vector addition and subtractions. So that is very attractive. Once again, we're learning from user actions. We're doing the update based on beta Bernoulli conjugacy. This is nothing more than the mathematical nicety that makes the update very simple to compute. And we're going to essentially use Thompson sampling, which has been empirically shown to minimize regret and opportunity cost in a 2011 URS paper. Subsequently, it's also being theoretically proven to have optimal bounds for discrete optimization. So in conclusion, we did end up succeeding in building and launching an AI-powered website that learns and optimizes UX over time. And I guess the key takeaway at this point is that if you're wondering if you can use OpenMined libraries to build production products, the answer is yes. Yes, you can. In fact, you can use the same algorithm to optimize your own website right now. So let's switch gear a little bit and talk about privacy and what that means for recommender systems. So the Rexus team was founded based on this demo and a key hypothesis. And that is privacy is something that will really enable recommender systems to both serve humanities and also improve company revenue. And here's how that will probably work. So imagine if you're able to provide differential privacy guarantees and only learn from private data that stays on the user's device. What this means is that companies will have ability to serve what people really want by understanding their customers better, because consumers are more willing to share private data when they understand that this data will be private. This will probably lead to better innovation, increased revenue, and lower friction in marketplaces and communities. And what this also means is that we get to potentially optimize for more things than just click-through. For example, individual or societal well-being. How would you do that right now? You can't really. Imagine if you're trying to optimize for someone's well-being, you may need to know information about their biometrics, for example, their cortisol hormone levels, or you might want to know about their deepest fears and anxiety if you're trying to help them in a mental health kind of setting. Right now, consumers have concerns about how this information is being used and how it could lead to harm. In a more practical example, imagine if you're trying to understand how much people are tipping their drivers when they get takeout, because we all do a lot of that, and you want to essentially send out a survey. People are more likely to inflate how much they actually tip, so you're not going to potentially get real data, and your data will be biased. But imagine if you tell the users, hey, listen, we're sometimes going to randomly just generate a number, and therefore we don't know if the number you told us is randomly generated or your actual value. So please go ahead and provide your real value. No one will find out how much you tipped, or if you're tipping too low, etc. This is just a very simple example of how you can use differential privacy to get better data. Another more interesting use case is something like, let's say you're building an organization that's trying to help underserved migrants or undocumented migrants, and you want to send them a questionnaire and have them answer. There will be a lot of concern and anxiety over what happens if this data gets leaked or gets subpoenaed, right? So you can imagine an argument where you say, hey, there's actually no validity in this data, and even if you wanted to get access to this data, it will not help you, because even though the data we gather is accurate in the aggregate and helps us help individuals, none of these individuals might have answered honestly. For example, if someone indicated that they're undocumented, this could actually just be a factor of the browser. Here's how that would look like. So going back to the browser, there's actually a secret feature that I haven't shown you yet. And here what we're doing is actually setting the differential privacy level, or differential privacy rates. So watch what happens. With the rate of 0.9, if you refresh again, it will automatically report a diff. As in, this is just the data sampled from the posterior that we have learned. And by doing so, it does not actually hurt the model, but it provides some level of plausible deniability. So let's change this back to 0.1. And maybe this user has less preference for privacy. This is now waiting for user input. So what this means is that you can either provide an update based on the posterior distribution that we have learned, which doesn't hurt the model, but provides plausible deniability and de-anonymizes the user in a way, or you could actually be learning from user updates and etc. So coming back to this, this is why we formed OpenMined Rexus. We want to build a future that has a equitable alternative to surveillance capital. And the way we're doing that is we're building open source tools and libraries for rapid experimentation for researchers. We're building these tools for ourselves because we're doing research, and we want to open source them to make it available for everyone. We want to enable rapid deployments to the real world because learning from simulated data is great, but the real world also always has surprises for us. And lastly, we want to empower engineers, companies to build products with differential privacy by default. All they have to do is download and import a library, and they don't need to go get a PhD or hire a whole research team. So current efforts include research, engineering, and products. Finally, I want to provide a call to action. If you're human, please consider if your data is being used fairly and to your benefit. And if you're not sure, ask questions. This is how you enforce accountability. If you're a company, let's collaborate. Please bring your use case, use our libraries, and let's build better privacy-preserving products together. And if you're a developer or researcher, we need you. Let's join forces. Thank you.